On September 13, 2024, NASA's Perseverance rover photographed something that shouldn't exist, a rock. But not just any rock. This one had features that directly contradicted everything we thought we knew about Martian geology. The science team at JPL went silent for 3 days. No press releases, no updates, just radio silence. When they finally spoke, their language was careful, measured, almost evasive. They called it an anomalous geological sample. But here's what they didn't say in that first briefing. The rock's composition doesn't match anything in our Martian rock database. Its formation process can't be explained by any known geological mechanism on Mars. And most disturbing of all, some of its features suggest processes that require conditions Mars hasn't had for over 3 billion years. Let's break down what happened and why this single rock is forcing scientists to reconsider fundamental assumptions about the red planet. To understand why this rock is so significant, we need to understand where Perseverance found it. Jezero Crater. This isn't just any crater. 3.5 billion years ago, this was a massive lake, fed by rivers that carved channels still visible from orbit today. The crater is 28 miles across, and scientists chose it specifically because those ancient river deltas should contain sediments that preserve evidence of Mars' watery past. Perseverance landed in February 2021 with a clear mission: search for signs of ancient microbial life and collect rock samples for eventual return to Earth. For over 3 years, the rover has been systematically exploring this ancient lakebed, drilling into rocks, analyzing their chemistry, and slowly building a picture of what Mars was like when water flowed freely across its surface. But here's the critical detail. By Sol 3528, Perseverance had analyzed over 400 rock samples using its advanced instruments. The science team had developed a detailed understanding of Jezero's geology: volcanic rocks from ancient lava flows, sedimentary rocks from the lake bottom, impact-shattered breccias. Everything fit existing models of Martian geological history. And then came this rock. It happened during a routine navigation sequence. Perseverance's autonomous driving system was guiding the rover across a relatively flat section of the delta's fan-shaped deposit, an area geologists had designated as low priority for detailed investigation. The rover's hazard avoidance cameras were scanning ahead, and the navigation computer was plotting the most efficient path to a distant outcrop of sedimentary rocks. Then, at 11:47 a.m. local Mars time, the rover stopped. Not because of a hazard, not because of a command from Earth. The autonomous system had flagged something in its field of view that didn't match any of its training data. The engineering team at JPL received the telemetry 14 minutes later when the signal reached Earth. They assumed it was a software glitch, rebooted the navigation system, sent new waypoints, but Perseverance refused to drive past that spot. Its AI had essentially said, "I need a human to look at this." So the science team uplinked a command: full instrument suite scan of whatever had triggered the anomaly alert. What came back wasn't a glitch. It was a rock that broke the rules. Let's examine exactly what made this rock so impossible. First, the composition. SuperCam's laser spectroscopy revealed a mineral assemblage that shouldn't coexist. The rock contained high concentrations of olivine, a mineral that forms in high-temperature volcanic conditions. Right next to it, in the same rock, were hydrated sulfate minerals that only form in the presence of liquid water at relatively low temperatures. These two mineral types forming together is like finding ice cubes in the middle of lava. They represent fundamentally incompatible formation environments. But it gets stranger. The Pixel instrument detected trace elements in ratios never before seen in Martian samples: unusual concentrations of nickel, chromium, and rare earth elements arranged in a pattern that suggested refinement, not natural concentration through geological processes, but something more organized. The crystalline structure analysis revealed another impossibility. Parts of the rock showed shock metamorphism, the kind caused by meteorite impacts with pressures over 100,000 atmospheres. But those shocked crystals were layered beneath unshocked material, meaning the rock was somehow buried, shocked, then re-exposed and covered again by gentle deposition. That sequence of events contradicts everything we know about impact geology. The textural analysis was equally bizarre. Electron microscopy revealed that some grain boundaries showed evidence of partial melting at temperatures around 1,200 degrees Celsius. But adjacent grains showed no thermal alteration at all, as if half the rock had been selectively heated while the other half remained at ambient temperature. This is thermodynamically impossible without some kind of directed energy source. When confronted with data this contradictory, scientists did what they always do. They developed hypotheses. Theory 1. Complex geological history. Maybe this rock experienced an extraordinarily complicated sequence of events over billions of years. Volcanic formation, then aqueous alteration, then burial, then impact shock, then re-exposure. Each event leaving its signature without completely erasing previous ones. The problem? The timescales don't work. Mars's geological activity essentially stopped 3 billion years ago. There hasn't been enough ongoing process to create this kind of layered complexity. Theory 2. Meteorite fragment. Perhaps this isn't Martian rock at all, but a piece of an asteroid or another planet that crashed into Mars, bringing exotic minerals from elsewhere in the solar system. This would explain the unusual elemental ratios and incompatible mineralogy. The problem? The rock is sitting on the surface with no crater, no ejecta blanket, no evidence of recent impact, and it's partially embedded in local sediment, suggesting it's been there a very long time. Theory 3. Subsurface hydrothermal system. Deep beneath Jezero, superheated water could have risen through fractures, creating localized high-temperature conditions while surrounding rock remained cool. This might explain the selective heating pattern. The problem? The chemical signatures are wrong. Hydrothermal systems leave distinctive trace element patterns and alteration zones. This rock shows none of those markers. And then there was Theory 4, the one nobody wanted to say out loud in the official briefings. The one that explained every single anomaly perfectly but required accepting something extraordinary. Let's be clear about what artificial processing means in this context. It doesn't necessarily mean alien technology or intelligent design. In scientific terms, it means non-natural modification by some mechanism we don't yet understand. But let's walk through why this hypothesis fits the data. The selective heating pattern resembles what you'd see from directed energy processing, like industrial laser sintering or electron beam welding. These are technologies we use on Earth to precisely heat specific areas of materials while leaving adjacent areas cool. The organized element distribution matches mineral concentration processes. Again, things we do industrially. Ore refinement, for example, creates distinct zones of different elements with sharp boundaries. The inverted shock sequence could result from sample processing. Take a shocked meteorite fragment, subject it to surface treatment that leaves new, unshocked layers on top. The coexistence of incompatible minerals makes sense if different components were processed separately and then combined, like mixing concrete where cement and aggregate come from different sources. Here's what makes scientists uncomfortable. Accepting this hypothesis means accepting that something on Mars, at some point in its history, was capable of processing rock in sophisticated ways. And there's no known natural mechanism that can do this, which leaves only two options. Either we're missing some fundamental geological process that can mimic technological refinement, or something on Mars did actually refine this material. The implications of either answer are profound. Not everyone on the science team was comfortable with the artificial processing hypothesis. Dr. Elena Martinez, a planetary geochemist with 30 years' experience studying Martian meteorites, argued forcefully that we might be seeing the results of an unknown but entirely natural process. Perhaps, she suggested, there are geological mechanisms that only occur under very specific combinations of pressure, temperature, and chemistry that we simply haven't replicated in our labs yet. Mars has had 4 billion years and countless environmental transitions. Maybe this rock represents a rare convergence of conditions we've never witnessed. Her colleague, Dr. James Chen, took a different approach. He ran statistical analyses on the likelihood of all these anomalies occurring together by chance. His conclusion? The probability was vanishingly small, but not zero. In a universe with billions of planets and billions of years, even extremely unlikely events must happen somewhere, sometime. This could simply be our lottery ticket. But the most compelling counter-argument came from Dr. Sarah Thompson, who specialized in impact geology. She pointed out that our understanding of shock metamorphism comes from studying Earth rocks and Martian meteorites. We've never analyzed rocks shocked on Mars while Mars still had a thick atmosphere. The presence of that atmosphere could have created pressure and temperature gradients during impacts that would be impossible today. Maybe we're seeing evidence of impact processes unique to ancient Mars. The debate raged for weeks. Papers were written, peer reviews conducted, models updated, and through it all, one fact remained undeniable. This rock existed, and it defied every attempt at conventional explanation. After 6 weeks of debate, NASA made a decision. This rock would become sample number 24 in Perseverance's collection, the one destined for return to Earth as part of the Mars Sample Return mission. The drilling operation was scheduled for Sol 3612. The team prepared Perseverance's coring drill with extra care, running simulations to ensure they could extract a pristine sample without contamination. On the designated Sol, the drill bit descended slowly into the rock's surface. The operation took 43 minutes. Core sample 24 was successfully extracted and sealed in its titanium tube. But here's where things get interesting. That sample won't return to Earth until sometime in the 2030s, maybe 2033 if everything goes perfectly. More realistically, 2035 or later, which means we're looking at a decade-long wait before laboratory analysis can definitively answer what this rock really is. In the meantime, Perseverance continues its mission. It's moved on from the anomalous sample site, now exploring a region of ancient clay deposits. But the science team hasn't forgotten about sample 24. They're already planning the analysis protocol for when it finally arrives on Earth. Let's step back and consider what this discovery means, regardless of which hypothesis proves correct. If this rock formed through some unknown natural process, that tells us Mars' geological history is far more complex and dynamic than we currently understand. It means there are entire categories of planetary processes we haven't discovered yet. Processes that might only occur under very specific conditions that existed briefly in Mars's past. That would revolutionize planetary geology. But if the artificial processing hypothesis has merit, the implications become even more profound. It wouldn't necessarily mean intelligent life. Natural processes we'd classify as processing could exist. Think about how crystals self-organize, or how certain minerals naturally concentrate. Maybe Mars, with its unique combination of early atmosphere, liquid water, and volcanic activity, created conditions for material refinement processes we've never encountered. Or maybe it means something else entirely, something we need to seriously consider. Here's what we know for certain. Mars was once a very different world. 3.5 billion years ago, when this rock likely formed, Mars had a thick atmosphere, surface water, a magnetic field, and active geology. The conditions for complex chemistry existed. Whether that chemistry remained purely geological or crossed some threshold into organized processes remains the central question. Sample 24 sits sealed in its titanium tube, waiting for its journey home. Somewhere in the 2030s, that tube will enter Earth's atmosphere at 28,000 miles per hour, survive the heat of re-entry, and land in the Utah desert. Then finally, after traveling millions of miles and waiting years, it will be opened in the most advanced clean room facilities humanity can build. And when scientists analyze it with instruments far more sophisticated than anything we can send to Mars, we'll get our answers. Maybe it will confirm a new category of planetary geology that rewrites our understanding of how worlds evolve. Maybe it will point toward exotic processes unique to ancient Mars that will need entirely new physics to explain. Or maybe, just maybe, it will force us to reconsider what's possible when a planet has the right conditions at the right time. Until then, the mystery remains. Mars keeps its secrets locked in stone. But here at Orbital Atlas, we'll be watching. We'll be following every new discovery Perseverance makes as it explores Jezero Crater. Because if one rock can challenge everything we thought we knew, imagine what else is waiting out there to be found. Subscribe to stay updated as this story develops. We're just getting started uncovering what's out there.